back in 2 dimensions, if I had a vector like this, I could talk about the angle of the vector by looking at the angle that it made with the positive x-axis, and we call that theta typically. Now that we live in 3 dimensions instead of 2, I'm going to disappear, I'm pretty sure. You see a disembodied arm. If I have a vector in 3 dimensions, that doesn't really work anymore. I don't really have the angle, but what I do have is angles of that vector with each of the axes. So I have an angle with the x-axis that I'm going to call alpha, an angle with the y-axis that I'm going to call beta, and an angle with the z-axis that I'm going to call gamma, because that's next in line. As the Greeks go A, B, G. That's okay, we like them anyway. So I have not 1 but 3 direction angles for a vector in space. The way we're going to look at these, we know something about how to find cosines of an angle using a dot product. So I'm going to use my vector, which we'll call V, with 3 components, 1, V2, and V3. And we're going to look at the angle they make with the standard unit vectors that go in the direction of each of the 3 axes. Let's look at alpha first. The cosine of alpha, well, the cosine of any angle between 2 vectors, I'm going to get the dot product. So I'm looking at the angle between V and the standard unit vector I over the product of the magnitudes. See, V I defined as V1, V2, V3, and I is in the direction of the x-axis, so I get a 1 in the x place and zeros elsewhere. If I could get the commas and the subscripts straightened out, my life would be perfect. Divided by, okay, the magnitude. So the magnitude of V, I'm just going to call the magnitude of V. The magnitude of I, here's I, the magnitude of I, 1. Not even going to write that. Well, look what happens with the dot product then. I have V1, V2, V3, dot product with 1, 0, 0. So my second 2 components disappear, they're multiplied by 0. And I have cosine of alpha is just the first component, just the x component, over the magnitude of my vector. You might be able to imagine what's going to happen now if I'm looking at beta. I'm going to use the standard unit vector in the direction of the y-axis, j, which is 0, 1, 0. So I'm going to have only the second component over the magnitude. And for gamma, I'll use the unit vector in the direction of the z-axis, which is 0, 0, 1. So cosine of gamma is just the z component. So there we have our direction cosines. Fun fact about the direction cosines. Think about this. If I take the first one, cosine alpha, times the unit vector in the direction of the x-axis, which is I, and then the other 2 ditto. Like that. Have I gone off the edge yet? No, almost. If I do that, I get V1 over the magnitude of V plus V2 over the magnitude of V plus V3 over the magnitude of V, each times their respective unit vectors. That one's in the I direction. And then we're going to actually add them. But when I do that, the denominator, the magnitude of v, is a scalar, so that doesn't change. The top, I get v1, v2, v3, the vector, which is b. So I have the vector v divided by its magnitude. That's a unit vector, by definition. And that means, if that's a unit vector, if I take its magnitude, I get 1, because the magnitude of a unit vector is 1. That's what makes it a unit vector. Which means the magnitude of this top line here well, we'll find the magnitude of that the way we find the magnitude of any vector, which is by squaring the components and taking the square root. The magnitude, it's a unit vector, so its magnitude is 1. That's true for any vector, regardless of what alpha, beta, and gamma are. Let's throw some numbers in there and look at a specific example. Let's use the vector 2, 3, negative 6. And I want to know the direction cosines for this vector. Well, we really already did all of the legwork, so we don't have to go through that whole process again. I know that cosine of alpha, the angle that that vector makes with the x-axis, is the x component over the magnitude of that vector. Well, let's see. That's, I'm going to have a 4 and a 9 and a 36. And hopefully you have that added up already. I don't, but. Seven? Wow. Sure is. Magnitude is a whole number. How about that? So cosine of alpha is the first component over the magnitude. Cosine of beta is the second component over the magnitude. Cosine of gamma with the z-axis is the third component, divided by the magnitude. So there are my direction cosines. Just for fun, let's try this out. I should get, when I square each of those and take the square root, I should get 1, because I've produced a unit vector here. If you want to know what the angles are, grab your calculator. You can do some arc cosines. I'm not going to do that, but your calculator will tell you if you want to know what they are. So we're going to do 2/7 squared, 3/7 squared, and negative 6/7 squared. Got 4 plus 9 plus 36, much like we have right here. Or no, but yeah, 4 plus 9 plus 36, which does not total 36. Totals 49. And we do, in fact, get 1. That's not a necessary thing that you have to do. I just think it's interesting. So look, it works. So direction cosines for a vector.